So welcome, Ralph and Jordan and Jesus. This is Friday of week 7, and today is yet another day in linear algebra, and we're going to do more on eigenvalues and eigenvectors. So let me share my screen and talk about what the agenda is for the day. Okay, so it's actually kind of a light day in terms of material. I think you'll enjoy that. There's even a chance we'll finish early, but I always say that and it never happens, but you never know. So I'll start out with questions as always. So if you have any questions when I finish talking about the agenda, I'll answer your questions. And then we'll do a little review of eigenvalues and eigenvectors, kind of remind you about what happened last time, kind of the main points, because eigenvalues and eigenvectors, they're definitely the most important part of the class in terms of applications. In terms of when I see applications, it's hard for you to understand that now, but you trust me on this one. They're big, but they're only in advanced classes. You would never, ever see them in I don't know, a sociology class, but definitely could see them in lots of engineering classes and physics and stuff. So after that, we'll get into practice on finding eigenvalues and eigenvectors. Just a minute, I just forgot I have my microphone off. Okay, so hopefully that helps sound-wise. And then after that, we'll practice some more, because eigenvalues and eigenvalues are so important. It's really important we get these down and you know how to find them, you understand what they do, what they're all about, and we're going to be using them a lot, and you'll use them after this class. Then we'll talk about, this is a little confusing, is similar matrices. So there's lots of different ways of defining similar matrices. So this chapter, we're going to talk about similar matrices, and there'll be a definition of a similar matrix, and we'll talk about how that relates to eigenvalues and eigenvectors. Okay. And then coming back, we haven't done this in a week or so. The following are equivalent. So guess what? We're going to add on one more. And as you probably could guess, it's going to have something to do with eigenvalues and eigenvectors. Okay. Particularly, it'll have to do with eigenvalues. And then if we have time, and I think we will, I'll do something that I do in my regular face-to-face class, and I think it'll work on this screen. We'll find out. Is I'll show you a kind of an application video, a video of another professor using eigenvalues and eigenvectors that aren't from this class. I don't know if you remember way back when we actually were in class, I used to do that. And I thought, since we might have some extra time today, it would be a nice to do also. It's a physics application, and it is something that if you take upper division physics and graduate level physics, you might see. So it's not first and second year physics, that's for sure. So that's the plan today. I want to mention one more thing, and that is a heads up about Monday. Is I apologize in advance if I'm a bit out of it on Monday. Any guess on what's happening on Monday for me?
Second COVID vaccine?
Yep, second COVID vaccine. I'm getting it at like 9:40 in the morning. And usually it takes a day to really knock you out, but who knows? So I want to give you that warning just in case I'm not myself. That's the reason on Monday. But I'll probably be smiling a lot more than usual because I'll be done with the vaccinations, which will be great. So, everything goes well, and I'm still feeling well a few hours after. but figured I should give you a heads up in case I look a little different than usual in terms of my energy level. So hopefully it's fine. Usually it takes a day, and then day 2, that Tuesday, if you come to my office hours on Tuesday, you might see me going, oh yeah, I guess so. That kind of stuff. But we'll see, because I've heard some really tough things about the second shot. So that's what I have to say in terms of the agenda and the heads up. The test isn't coming for another few weeks, so I don't have to go there yet. But if you have questions, this is a great time to ask a question.
Did you see that Perseverance landed successfully yesterday?
That was awesome. That was really awesome. And given the fact that I've had friends actually were involved in Mars rover stuff, it's pretty cool. So now I think next month, they'll be sending out a drone. We'll have a helicopter on Mars. Kind of cool. So, and there's probably some linear algebra used, but I can't tell you for sure. Because definitely you want to do some kind of spatial changes and look at rotations of the Mars and stuff like that. We'll talk a little about that today. So
What was fascinating to me about it is it was entering the atmosphere at almost 12,000 miles per hour.
yeah, remember
Like-
their atmosphere is not the same as ours, though.
Yeah, and I just find that so fascinating that they were able to get it to decelerate enough to land successfully. It's impressive.
That was the amazing thing. Yeah, and it worked. And again, I promise you, there's an intense amount of mathematics involved in it, and there's got to be linear algebra. It's not my expertise, but I know there's got to be. So pay attention to your math classes. Any questions? Any other questions? Homework problems that you want to see done? I'm looking at a blank chat box, but it'd be fine if you popped it in there or if you said something.
Yeah, can we do 5.9? I think it was 1. Yeah.
5.9 number 1. Okay, let me go find it. Okay. The interesting thing about 5.9 number 1, which I'll pop in a moment, it takes me a moment to do that, is that you actually don't need this section at all to be able to do 5.9 number 1. We did this a long time ago because it happens to be homogeneous. But we'll look. Okay, so here's 5.9 number 1. So it says, write a solution set of the following system as a linear combination of vectors. Okay, and as I just mentioned, notice that the right-hand side is the 0 vector. Okay, and that makes it just kind of like an easing into the rest of the problems question. So what we're really just doing is finding the null space of this matrix. Do you agree?
Yeah.
Okay, so do you remember how to find the null space, or if you like the word kernel, whichever word you like is fine. What is the first major step after looking at the question to find the kernel or the null space?
RREF the matrix.
Exactly. Is that clear so far? And that's because a long time ago we had a theorem that said if you have a homogeneous equation, then the RREF has the same, or if you have a matrix, the RREF of the matrix has the same null space as the original matrix. Do you remember that theorem?
Yeah.
That's an important theorem. So that means if we RREF it, it'll simplify it immensely. Okay, is that clear? All right, what I can't do is do this in my head. I mean, I could do it by hand, but my guess that's not the issue you have, right?
Yeah, my issue isn't with the RREF.
Okay.
I think my issue is partially addressed already. I just didn't make the connection between this and kernels. So
because I could finish this up pretty quickly, especially if you tell me, because you're probably
I'll put it into an RER calculator.
I bet some of the others of you have done this also. Maybe you already have the RREF matrix sitting written down on your piece of paper.
Yeah, I got it.
And as you can see, as I'm going, I'm putting a matrix in. Okay, so what is the RREF of A? Let me write down RREF of A equals. And what is it?
So red as rows, it is 103.
Okay. You can talk faster than I can type, so
And then 0, 1, 1.
0, 1,
And then
1.
the last row is zeros.
Yeah. Okay. Does that make sense so far? Okay, so we're trying to find the null space of this matrix. And the nice thing is this thing, what is the dimension of the null space? Just by looking at the RREF matrix.
2.
One more guess.
1.
1. There's one free variable. Do you see that? The third variable is the free variable. There's 2 pivots. So the rank is 2. And remember, the rank plus the kernel, plus the nullity, sorry, is equal to n, the number of columns. There's 3 columns, 2 pivots, 1 free variable. So that means we just need 1 vector. And just to make it easier to type, I'm going to write it as a row vector. So to get that 1 vector, well, the free variable is the third variable. So let's let that be 1. So the first row says that x plus 3z equals 0. If z is 1, x is -3. Any questions on that basic arithmetic or basic algebra, I guess? Okay, the second row says y plus z equals 0. So that means y is -z. If z is 1, y is -1. And the third is 1 because we let z be 1. That was our free variable. Any questions so far? Okay, so that is, let me just write down the kernel of A is equal to the span of the single vector. So now it says write down, write the solution set of the following system as a linear combination of vectors. Okay, of course, the grammar is wrong. Why is the grammar wrong? Yeah, there's only 1 vector, so it should be of a vector, but that's because they didn't want to give it all away. So what we can say is that the solution set is equal to, well, now we write down as a linear combination. If there's only 1 vector, there's not a whole lot to write. But I do have to turn it into math mode. So it's C1 times -3, comma, -1, comma 1. Did I lose you anywhere? Any questions on?
No, I still think I think I'm following.
Yeah, and that's it, we're done.
Okay.
When there's only 1 vector, there's not a whole lot to write.
So for all of these, if it's equal to 0 like that, you would find the null space and then multiply it by a constant C1 or something.
Right. And if there were, but remember, if it was a 2-dimensional space, you get C1 times the first plus C2 times the second.
Yeah.
So however many you have, you stick some C's in front and put some pluses. But when you only have 1, there's not much to do. Now, if you don't have equals 0, then what you would have to do is you would find one solution vector and take that and go plus the constant times the vectors. But in this case, we had equals 0. So we don't need to find a particular solution because the particular solution is just 0. Any questions on this? Does that make total sense or is that confusing? Okay, other questions? Other questions? Give you a second or two. Okay, if there's no questions, then I'll move on. And again, we kind of have a light day today. So just kind of the way it works sometimes. I didn't want to push all of the section in with the other section on Wednesday because eigenvalues and eigenvectors are too important. Let's see. You just let z equal 1. Yeah. And that's why, remember, we call it a free variable. Free means we are free to choose whatever number we want to choose it to be, except 0. You can't, if it's only a single number, you can't choose it to be 0. You can't choose all of them to be 0. So that's it. So I could have chosen 20 if I felt like it. Would have made the numbers messier, but I could have. So I choose 1. The only time I don't choose 1 is when there's fractions, and then often I'll choose the number to be the common denominator, so you don't have to deal with fractions. That gets rid of fractions usually. But here there's no fractions in the RREF, so 1 is good. Okay. So for example, if this 1 and this 3 were switched, then you might choose 3 to be the free variable. But in this case, we just have 1s here and no fractions. We're good. Okay. All right, well, let me talk about new stuff, and actually a little recall before I get to new, because it's so important. I want to write this again. Okay, this is, we have a whole chapter just in eigenvalues and eigenvectors because they're so important. Okay, and by the way, it's not just the way I feel. The author made it a whole chapter too, and it's just one concept. So it's not a lot of concepts. It's one of the easier chapters, but one of the most important chapters. Okay, and let me remind you of some of the definitions that we had on Wednesday. First, if lambda is an eigenvalue of A with eigenvector V, I should say if, typo, if AV equals lambda V. I just want to give you a warning. The book uses X. I like V for vectors, so I tend to, if I can, I use V. So I apologize if that's confusing for you, but I just like that letter better for vector because first letter of the word vector. And X could be a little confusing sometimes because is that a vector? Is that a number? So I use V. Okay, maybe it's because the way I learned too, but I like it better. So AV equals lambda V. So just note, in terms of geometrically, notice that A is a linear transformation. Okay, you can think of a matrix multiplication as a linear transformation. And it's a linear transformation on Rn. So the question is, what does it do to this vector? Well, it multiplies it by a constant. So geometrically, we can think of a vector, especially in this case, as part of a line. And you could just look at the line. And if you take a line and multiply by the line by a constant, right? So if you take all the points on a line and multiply those points by a constant, and the line goes to the origin, what happens to the line?
Expands into a plane.
No, it doesn't actually. If you have y equals x, and you take all the points and multiply by a constant, what happens to y equals x? If you have 3y equals 3x, what do you have now?
You have a bigger tree, a constant multiplied by those, right?
But what happens to the line?
It gets larger.
Lines don't
It
have
undergoes a
size.
linear transformation.
The lines don't have size because they go out forever, right? So now think about the vector and think about the line, like y equals 3x. What happens if you multiply x and y by the same constant? If you take y equals x, turn it into 3y equals 3x, what have you done to the line?
Nothing.
Exactly. That's what I was hoping for. Nothing. 3y equals 3x is the same as y equals x. Do y'all agree?
Yeah, because you divide by 3 and voila, you're back where you started.
Right. So now let's look at this AV equals lambda V. Well, what we're doing is we're multiplying y and x by the same number. Because remember, V is y comma x, or x comma y, sorry, it's probably better. So V is x comma y. If you multiply both x and y by a constant, you haven't changed the line at all. Do you agree? So what this means is that the line that V lies in, or determined by V, is a fixed line. Okay, the line doesn't change. Any questions on that? So whenever you have a matrix thought of as a linear transformation of the plane, for example, then if it has an eigenvalue, then the line that the eigenvector, the corresponding eigenvector sits on, doesn't get changed by the linear transformation A. Okay, so that's the geometry. That's the geometry of this. Okay. Whereas if there are no eigenvalues, is it possible there could be no eigenvalues?
Probably.
Yeah, the word is actually probably is close, but depends is a better word. It depends on what your universe is. So is 3 plus I a number or not? And it depends, right?
Yeah, it depends.
It depends. So if you only want to live with the real numbers, then a matrix cannot have sometimes not have any eigenvalues, right? Because remember, there's a characteristic equation, and the characteristic equation may not have any roots, and the roots are the eigenvalues. Okay, so in particular, if there's no roots to the characteristic equation and you have no eigenvalues for the matrix A, that means there's no fixed lines. Okay, can you think of an example of a linear transformation that doesn't fix any lines? Kind of in words. I'm not looking for the matrix. I'm looking for some words. One word, actually.
Identity.
Actually, the identity fixes all lines because it fixes everything.
It's just a 0.
The 0 kind of fixes a line because if you're on the line and you get sent to the origin, you're still on the line because the line goes through the origin. Does that make sense? That's a little tricky or technical. There's something better. It's a one-word answer. It starts with an R. If you think about what matrices can do to the plane. Any thoughts? All right, maybe I'll say it. Rotation. So if you have remember, a matrix can rotate the plane. Do you remember that? So if it say rotates by an angle of pi over 4, then no lines are fixed, right? And if no lines are fixed, that means that you don't have any eigenvalues. Okay, at least no real eigenvalues. Any questions on that? Any questions? All right. Do you think this comes up in applications, like not have, an example of a matrix not having real eigenvalues, but those complex eigenvalues are still important? What do you think? Yeah, a lot. So let me tell you one that you would probably never guess. Music. Do you realize, I think I'm the only person I've ever met that when I hear music, I think of matrices and differential equations, actually, but the matrix is the solution. And I can actually see in my weird mind, I can see the matrix, and I can see that I know that the singer usually, or the writer of the song, probably wasn't thinking about matrices, but in there deep ingrained, there's a matrix. And it turns out that you can do that. Okay. And so that's one example that's kind of fun. But there's lots and lots of other examples. Electrical engineering is another example, is that if you have a circuit, then there's some kind of wavelength solution, And that's going to be, again, the eigenvalues of a matrix. And you just trust me on all this. You get that next quarter. So I can't explain it all to you because you need differential equations to understand it. So that makes it a little tough. Sorry about that. But I want to let you know that it's everywhere. Okay, but you have to really understand a lot of math. You need one more, you need at least one more course to really get it. Any questions on what an eigenvalue and an eigenvector is? Okay, and then remember that the characteristic polynomial is the determinant of a minus lambda I. All right, just note, what is the determinant of a minus lambda I is a polynomial. Otherwise, we wouldn't call it the characteristic polynomial. What's the degree of the polynomial?
Depends.
What
on
is
the
it?
matrix.
And what is it? And what does it depend on? What part of the matrix, or what aspect of the matrix does it depend on?
Its dimension.
Yeah.
Yeah, the column count.
Yeah, column count. And remember, column count and row count's the same because we can't even talk about eigenvalues and eigenvectors unless you have a square matrix. So if you have a 4x4 matrix, you get a degree 4 polynomial. Do you agree?
Yeah.
Okay. If you have a 5x5 matrix, this should be easy. What degree will the polynomial be?
5.
Okay. And by the way, if you have a fifth degree polynomial, if it's a second degree, you can use a quadratic formula. If it's a fifth degree, what can you use?
A computer.
Yeah, maybe.
Calculus?
And the answer is nothing. It's actually been proven that there is no formulaic way of solving a fifth degree polynomial or higher. So I want to let you know that, it looks really easy to say, oh, you just take the determinant, you get a polynomial, and then set it equal to 0 and solve. Sounds easy, right? Until you start trying to do one, and then you realize, good luck. What you can do is you can approximate it using, say, Newton's method. Do you remember that last year? Remember that happening? I know it's been a while, but so Newton's method happened a year ago, more than a year ago. And so that's one way, kind of a main way of approximating the eigenvalues is using Newton's method, because you're going to get a high degree polynomial. Okay. On the other hand, if you do 1x1 matrices, those are really boring. Okay. They're really boring. In fact, what are the eigenvalues of a 1x1 matrix?
That number.
Yeah, probably.
That number, because you just have the determinant of the number minus lambda. Well, guess what? You take the number minus lambda, set it equal to 0, and you get lambda equals a number. Okay. So no one ever talks about, I've never seen anyone talking about one by one matrices because they're just dumb. Do you agree? So what's the next one that we might be able to do? Because 1-to-1 are just ridiculously stupid.
2x2.
2x2. So this is where I'm going to have you try. So here's an exercise. I want to give you about 3 or 4 minutes. It's going to take some time. Okay. It's not brutal, but it might take a little bit of time. I don't necessarily want you to find the eigenvalues, but I want you to find the characteristic polynomial for the general 2x2 matrix ABCD. So I want to give you a couple minutes. Shouldn't take more than 2 minutes to do. You don't have to solve it, although you should all know how to solve it once you're there. But let's see if you can do that. So, and if you have questions, I can answer, but hopefully you can just jump in, subtract the lambda I, take the determinant, and get there. Okay. And then write it as a polynomial, like, some number times x squared plus some number times x plus some number equals 0. So I'll give you a minute or two because it's actually really important. And beautiful when you're done, if you understand beauty well enough. And when you're done, put it in the chat box. Okay, I want you to multiply it out. I want you to write it as something times lambda squared plus something times lambda plus something. Okay, which is basic algebra, but hopefully you can FOIL and combine like terms. But there's a reason I'm asking you to do that, because it's a nice form. All right, Bradley, you should also factor out the lambda, or something times lambda, not something times lambda plus something times lambda. You're close. Because there's a reason why I'm being picky, and you'll see when I'll do it, and you'll see. So what both of you have is correct. It's not in the form that's what we need. Lambda, a. There's an extra lambda there, kind of. Because notice the BC and the AD don't have a lambda. So you want something times lambda, you want something times lambda squared, or just lambda squared, and then plus or minus something times lambda, and then plus or minus something. Getting there, though. And I'm okay if you spell lambda wrong. All right, let me work this out, because I don't think all of you are following what I'm asking for. Okay, so what we're going to do here is, let me copy and paste it. We don't want A, we want determinant of A minus lambda I. Okay, and lambda, by the way, is LAMDA. You don't need to know that. I would never test you on it, but just in case you're interested. But if you write LAMB, I'm okay with that. So determinant of A minus lambda I is equal to determinant of A minus lambda BC D minus lambda. Any questions so far? That's equal to A minus lambda times D minus lambda minus BC and that is equal to lambda squared and then notice we have a minus A lambda and a minus D lambda. So I'm going to write that as a minus A plus D times lambda. And then we're going to have a plus, And then we'll get an AD minus BC. I'm going to put that in parentheses. And that's a characteristic polynomial. I'll set that equal to 0 because that's what you usually do. Any questions on that? All right, now we're going to look at this. This is why I wanted you to write it this way. What is A plus D? Look at this matrix. We have a name for A plus D. What's the name of that? Do you remember? Remember when you add the diagonals, what do you call that? None of you are jumping in. Remember, that's called the trace. I'll write TR of A. So the trace of A is the sum of the diagonals. Happened in like an exercise. What about AD minus BC? What is that one?
That's just the determinant.
Yeah. So this is a very important formula, and it's not that hard to remember. That's what I like about it, is that when you have a 2 by 2 matrix, the eigenvalue, the characteristic equation is lambda squared minus the trace of A times lambda plus the determinant of A. Okay. By the way, does this always have a solution? What do you think?
Depends.
Yeah, it depends on what you call a solution. So what we can say is that if you're looking for real solutions, it'll have a real solution whenever the trace squared minus 4 times the determinant is non-negative, right? That's just the discriminant, the quadratic formula discriminant. Whereas if the trace squared minus 4 times the determinant is negative, then you get 2 complex roots and you get 2 complex eigenvalues. And if the trace squared minus 4 times the determinant equals 0, then that means you get a repeated, you get a single eigenvalue. Okay. Any questions? Any questions on this big idea? Notice this is not like a very specific example. This is all 2 by 2 matrices. This always works. Do you think there's something similar to this with 3 by 3?
No.
One more guess?
Yes.
Yes, there is. But it's not just trace and determinant. It's a little fancier. So I'm not going to get into it. And then you can actually do n by n, and that gets even fancier. Okay, and that has to do with all kinds of interesting factorials and stuff, permutations and combination type of stuff, which I'm not going to get into because I can only do so much. But for 2 by 2, this is nice and pretty, isn't it? Any questions on the general 2 by 2 matrix and the eigenvalue? By the way, if there's an eigenvalue, is there always an associated eigenvector? What do you think?
Yes.
Yeah, the answer is yes, because that's the whole point, is that if there's an eigenvalue, that means that the eigenvector is the null space for A minus lambda I. And if the determinant of A minus lambda I is 0, then there's a non-trivial null space. That way we had a theorem about that weeks ago. So the answer is, this is really important to note, is that if you're looking for real values, then you always get an eigenvector for every eigenvalue. Okay. So it gets a little more complicated in terms of the dimension, but we're not there yet. We'll get into the eigenspace, the vector space of eigenvalues, but not today. Another day. Any questions on this idea of this exercise example? But really, it's all of all 2 by 2 matrices I just did. or we just did. Okay. So as I mentioned, if there's only complex eigenvalues for a 2 by 2 matrix, then the transformation is a rotation. Since lines to the origin are mapped to lines to the origin, and that matrix is going to rotate the lines so that they don't hang out in the same line. There's no line that stays the same. All right, one more exercise. So today I'm having, since there's not much for me to talk about today, I figure I'll have you guys practice and then I'll do it and we'll follow along. You can answer questions. Let's see it. Now let's do a 3 by 3. And as I mentioned, the formula for 3 by 3 is really messy, harder to you can't just memorize it so easily. So there's one, just do one. I think it's good practice. Let's see if you can find the eigenvalues and eigenvectors for this matrix. 1, -1, 0, -1, 2, -1, 0, -1, 1. So first, we're going to do this in 2 pieces. And this should be obvious. What are the 2 things you have to do?
Find determinant of lambda I minus A.
You're making it way too hard. What are the 2 things? Look at the question.
Find the eigenvalues.
Yeah, so one thing is find the eigenvalues, and the second is find the eigenvectors. So what I want y'all to do is see if you can by hand find the eigenvalues for this matrix. And pop them in the chat box. And then we'll do eigenvectors, but let's do one at a time because otherwise we'll be sitting here in silence too long. Because 3 by 3 takes some time. And this one's going to be a bit messy, and I'm going to let you know, I guarantee that the numbers are nice, and that's important because it's a 3 by 3 matrix, which means you're going to get a third degree polynomial. And if the numbers aren't nice, boy, it's hard to find the roots. So I promise you the numbers are nice, which means you can, hunt and peck once you get to the polynomial. So give it a shot. I'll give you a few minutes to find the eigenvalues. And if there's an eigenvalue with a higher multiplicity than 1, you can either write it twice or you can state its multiplicity. I think it's worth it to put it on another page. So if you have questions, if you get stuck anywhere, let me know. And when you do come up with the values, put them in the chat box. And we want to at least have 2 people agree. Any questions? So you got to brush up on your old algebra skills and not linear algebra. This is actually, this is a section where we do nonlinear algebra to do linear algebra. Hopefully you're getting close. Maybe I'll write the first step down. Oops. Hopefully you all got that for the first step. Determinant of, you take the A and then you subtract lambda I, which means subtract lambda from each of the diagonal entries. Take the determinant, set it equals 0. As you're working, maybe I'll do some more steps. I don't see y'all dropping into the chat box. Maybe I'll guide you through it because it's been a bunch of minutes. So you take the determinant, and it turns out you can choose whether you want to expand about the first row or the first column. You do others, but you always go for the 0 if you can. I guess you could do the third row or the third column. That'd be fine too. But I'm just going to go to the first column. 1 minus lambda is that entry in the first column. So I put that there. It's in the 1, 1. 1 plus 1 is 2. Negative 1 of the 2 is 1. So that one just hangs out. Ralph got the same as Jesus, so we'll see. Okay, and then you take the determinant of the minor, which is 2 minus lambda times 1 minus lambda, minus negative 1 times negative 1, which is minus 1. And then we go to the next one, and that's going to be negative 1 times negative 1 to the 2 plus 1. So it's negative 1 times negative 1, which is positive 1, so I don't need it. And then you take its minor, and that's negative 1 times 1 minus lambda. And then, oh, you know what? That should be a minus 0. Because we got rid of that one. We got rid of that one. We get negative 1 times 1 minus lambda. And then 0 times negative 1, obviously, is just 0. Any questions so far? Okay, let's continue on. Oops. So now let's get to the next, simplify or multiply it out. So we get 1 minus lambda. And actually what I can do here is I notice I have a 1 minus lambda in the first term, and I have a 1 minus lambda in the second term. I can factor that out. The zeros just hang as zeros. So I can write down as 1 minus lambda. It makes life a lot easier. 1 minus lambda times, and now see what's left. So we have 2 minus lambda times 1 minus lambda minus 1, and then plus negative 1 times 1 minus, plus negative 1. So that gives me 2 minus lambda times 1 minus lambda. And then we have a minus 1, minus 1, minus 2 equals 0. Any questions so far? Okay, so now we continue on. So we have a 1 minus lambda, keep that factored out. The whole point is we want to factor things when you set things to be 0. So 1 minus lambda. And now let's multiply out the rest. I get a lambda squared and then I have a minus 3 lambda. And then I have a plus 2. So I have a plus 2 minus 2. See if I did this right. Any questions on that? Equals 0. So what's lambda? I'm a little worried because I don't think this is right. Anyone see a mistake? So 1 minus lambda, 2 minus lambda, 1 minus lambda, minus 1. That looks good. And then for this one, you get a 1 times negative 1 times 1 minus lambda, period. Take out that. You get 2 minus lambda times 1 minus lambda, minus 1, minus 1. So 2 minus lambda times 1 minus lambda minus 2. Any questions on this? I'm a little worried because then I get the 0, 1, 3. Because now lambda squared minus 3 lambda is lambda times lambda minus 3. So then we get lambda equals 0, lambda equals 1, or lambda equals 3. So are you convinced that this can get quite messy?
Yeah.
Imagine if it was a 10 by 10. Okay, so just a warning. Even computers can get stuck because this can get really nasty because it's of order n factorial, where n is the number of entries in the matrix. So as soon as you get a big matrix, computers don't like it. Like 20 by 20 is not good for computers. 20 factorial is too big for a computer. Any questions on this idea? Okay, again, I don't want to waste your time on just a bunch of algebra, but I did want to emphasize that this has a bunch of algebra. Okay, I'm not going to do them all, but let's do lambda equals 1. And let's find the eigenvector for lambda equals 1. How do you do that?
Just plug in the lambda.
Right, we plug in lambda equals 1 into this matrix here. And then find the null space. So if lambda equals 1, this 1 minus lambda becomes a 0. The 2 minus lambda becomes a 1. And then the 1 minus lambda becomes a 0. And I can get rid of the bottom. That becomes a 0 if I do a row op. Is that clear? Maybe I should show the work for y'all. So now we're going to take -1 times row 1, add it to row 3, and replace. That becomes a 0. Let's switch the rows. And when you switch the rows, we get that guy. Don't need the negatives there, obviously. -0 is right, but I don't want it. Any questions so far? Okay, now I could take this guy and replace row 1 with row 1 minus row 2. So that 1 becomes a 0. We can multiply row 1 by -1, get rid of the negatives. And now we're good. So what is our eigenvector? Let me write V. This was eigenvalue 1. So sometimes we write V1.
-101.
Yeah, -1, 0, 1. And there's our eigenvector. So that's how you find eigenvalues and eigenvectors, by hand. Okay, and I could do it for the rest, but I don't want to waste your time. Sound good? It's the same idea, though. Okay, I want to move on to a definition that's kind of a nice definition, nice important one. And that is similar. So we say A is similar to B. Sometimes you write A tilde B. If there exists an invertible matrix P with A equals P inverse BP. Now you look at that and yeah, you're like, sure, you know, it's a definition, but who cares, right? But let me tell you, this is a really important definition. So this is the big note that I have, which unfortunately I didn't see in the book. And it's like, come on, book. It's like the whole point. A is similar to B if and only if the matrix T with respect to the standard basis and B is the matrix T with respect to the basis with columns in P. Okay, so what that says is that if I look at the linear transformation that corresponds to A, and then what I do is I look at that same linear transformation, but I do it in the basis that has the columns of P. Then I end up with the matrix B, or vice versa. However you want to go, it doesn't matter. Okay, so let me tell you why this is so important, because in reality, does anyone tell you, like in 3D, what the coordinates of the universe are? Are there any natural coordinates for the universe? You know, where
No.
your X, Y, Z, you know, if you take the X, Y, Z axes, where do you put them in the universe, in our real universe that we have, that we're sitting in?
There isn't a center, right? So
Yeah.
they're nowhere.
In fact, I remember I was watching a physics course, and it just was an amazing fact that I'd never realized. I always thought, well, why don't we just let the center be the Big Bang? Right? Because isn't that the center of everything? Do you know why that doesn't work?
Because the Big Bang is everywhere, basically, right? It's like
Yeah.
an expansion sort of deal.
Yeah, it's a really weird thing. But even if you go there, there's no obvious place to put the XYZ axes. So there is no like clear way of putting axes. Okay, they can go anywhere you want, which means that you can change the bases. Okay, even if you know the center, even to say what direction should X, Y, and Z be, there's no natural direction. So what it says is that if you change the direction, if like I look at my axes, as long as we keep the same center, by the way, it turns out, I look at my axes and you look at your axes, even if they're not even right angles, as long as they're a basis, we're going to have the linear transformation that corresponds to the matrix is going to be the same no matter what basis you're looking in. Do you see how important that is? So everything we do, we always like, well, let's draw some X, Y, Z axes, but no one tells you, I mean, there's no like way that you should draw them, but it turns out it doesn't matter if you're going to call them similar. So that's why we call them similar. Any questions on this big definition? Now comes the big theorem. And that is, if A is similar to B, then A and B have the same eigenvalues, no matter what. Okay. What's left out here? They have the same eigenvalues. What should you be like, what else might be the same? Yeah, do you think they're the same eigenvectors?
No.
The answers are not. Okay, they're not necessarily the same eigenvectors, but the eigenvalues are always the same. Okay. So we want to prove this. I should prove something every day, right? Otherwise, it's not fair to you all since you have to prove things. Okay, well, let V be an eigenvector. Let lambda be an eigenvalue of A. Then, by definition, hopefully you all know, what's the definition say?
A of B equals lambda B.
Yeah, so A V equals lambda V. Right? This is one of those proofs that you just do what you think you should do and it's going to work. Any questions so far to start that out? Okay, now let me scroll so that you have the definition right up there. What do we know about A? If A is similar to B, what can we say A is?
It's B.
Yeah, it's P inverse BP. So since A is similar to B, what we can do now is we get a substitute. So I'm just going to copy and paste and replace our A. Any questions on this so far? So A is now P inverse B A. BP, sorry. Any questions so far? Okay, now if you want, we want the definition of an eigenvalue for B. And a definition for eigenvalue of B can't have a matrix to the left of B, right? Because we want B times a vector equals lambda times a vector. Do y'all agree? This P inverse is in the way. So how do I get it out of the way?
Multiply by P.
Yeah, multiply, and I'm gonna be more picky about than you are, and that is left multiply by P, because left multiplying and right multiplying are different, right? So if I left multiply by P, P inverse goes away, and I get P lambda V. Any questions on that? Okay, but lambda is a constant. Constant can always get pulled out. So P lambda V is equal to lambda PV. Any questions on that little linear algebra piece? Why am I done? You want to see? Let's just let, how about W equal PV? Remember, V is a vector, PV is also a vector. Let's give it a name, W, sound good? Then we can say that B times W is equal to lambda times W. Anyone lost on that? And that's the definition of an eigenvalue, is B times a vector is lambda times that vector. But notice that it's a different vector, is that we started with the vector V as the eigenvector, and now I have W as the eigenvector. Okay, so the eigenvector changes, but the eigenvalue doesn't change when they're similar. Okay, and it is possible the eigenvector doesn't change either, but usually it does. Any questions? Any questions on similar matrices?
If the eigenvector does not change, does that mean A and B are the same?
It's not quite.
Okay.
That's a little deeper, and I don't think we'll get to it another day, but it's too deep for this to do, and it's not in this section even. Yeah, so it means that part of the eigenspace is the same, but I think that's as far as I'm going to go. Sound good?
Yeah.
Okay. Any other questions? It's a good question, but it's like I said, that we'll get to it. We're gonna let me give you a heads up of why, what you really want, and that is if you have a basis that's not so nice. And when I say not so nice, if we have a matrix that's not so nice, then it turns out we can make it nicer. What's the nicest matrix there is? Let's say a 3 by 3.
The identity.
Identity matrix.
Okay, the identity. You can't, not every matrix is similar to the identity. For example, the 0 matrix is definitely not, because the 0 matrix has 0 as an eigenvector, as an eigenvalue, and the identity doesn't. So you can't always get the identity. So you can't be that greedy. Okay, what's the next easiest?
Standard basis.
No, what matrix? The matrix of standard basis elements is the identity. So you can't say that one. That's just repeating the identity. Anyone know? Okay, the next is diagonal matrices, where you have zeros, everything outside the diagonal, and you have numbers on the diagonal. And it turns out not all matrices are similar to diagonal matrices, but a lot of the ones that you use in the real world are. So what you're going to want to do is you're going to say, let's see if we can find a matrix, find a basis at which we start out with the matrix A, that's some messy matrix, maybe a 3x3 or 4x4 matrix. But then when we use the right coordinate system, it's diagonal. Because diagonals are nice, like the determinant. Hopefully y'all know, if you have a diagonal matrix, the determinant is easy to find, right? The eigenvalues and eigenvectors are easy to find because the eigenvalues are the diagonal elements. Okay, so everything is nice with diagonal. So the point, the whole purpose of this is to go and find a basis so that your matrix is diagonal instead of a mess. Any questions on that idea? Okay, so here's another theorem. And that is if V is an eigenvalue if V is an vector with eigenvalue 0, then V is in the null space of A. Why is that true? Why is that really easy to prove? Let's write proof. And I'll start let 0 be an eigenvalue for A with eigenvector V. What does that mean? So what can you say? Just from what I just wrote down.
We can say that A of 0 equals lambda B, or A of V equals 0 B.
Yeah, A times V equals 0 V. What's 0 V?
The kernel.
No, what's 0 times V? Very easy question.
0.
0, right? 0 times a vector is always 0. Hopefully you all know that, right? Well, guess what? If AV equals 0, what do you know about V?
It's in the null space of A.
Yeah, by definition. I'm done. Okay, and if you like kernel, you can say kernel instead of null space. That's totally up to you. Any questions? Isn't that beautiful and easy? So the eigenvectors corresponding to the 0 eigenvalue is the null space. Okay. So that tells us TFAE and the TFE, by the way. So I copied and pasted. I don't know if you remember, but we had 12 of them before. Now we have 13. So the big theorem of the entire class, TFAE. A is invertible. Determinant of A is non-zero. I'm sorry, it should be 0 is not. There we go. RREF of A is the identity. The columns of A are linearly independent. The rows of A are linearly independent. The columns of A span Rn. The rows of A span Rn. The rank of A equals n. The nullity of A equals 0. T is 1 to 1. T is on 2. T is an isomorphism. And now 0 is not an eigenvalue of A. So we now have another TFAE entry. I did warn you, we're going to get a lot, right? Any questions on why this is TFE? You know, why this works into it. Okay, the other way of looking at it, if you want to kind of prove it a different way, is that if 0 is an eigenvalue of A, then you could say determinant of A minus 0 is got to be 0. Well, guess what? The determinant of A minus 0i is just determinant of A. So the determinant of A is 0, and there we go. That was number 2. So you need it to be non-zero. If A is not an eigenvalue, that means the determinant must be non-zero. So that's kind of a proof right there. Any questions on the newest TFAE entry? I don't know if you remember when there were just 2 of them. Now it's starting to grow. Any questions at all on this TFAE? Okay, you ready to hear a little not me talk, someone else talk? So I'm gonna have to reshare. Let's do this. Which one is it? That one. There we go. Okay, so just note, let's full screen it. Let's see. Can you see the full screen?
Yeah.
Okay, because like I said, it's kind of new to me. I haven't shared a video before on Zoom. Hopefully it'll work. And I can't share the whole thing because it's 49 minutes long. But I will let you know. This might be easy for you. It's quantum physics. You guys are all experts in quantum physics, right? Just
I
kidding.
wish.
I'm just kidding. But here's what you might know. Have you heard about the spin of an electron?
Yeah.
Yes.
Yeah, and in fact, if you look at, let's say the, I don't know, the p shell or the s shell, the first shell, how many electrons can there be in that shell? In the first
Isn't
shell?
it like 6 in a p shell and 2 in the shell?
S.
Yeah, let's go to the s shell. I think is probably best. It's 2 in the s shell. Do you know why there's 2 in the s shell?
Because of the energy state of that orbital.
Yeah, you call an energy state, often called the spin state. So the spin state of that orbital can be either positive or negative. Sometimes they call it that. And what this professor is about to talk about is the spin state of an electron. And again, if you don't understand it, that's fine. You won't be tested. I definitely will not test you on quantum physics. But I thought you might be interested, like actually seeing what we're doing being used in. There are no lower. You'll never see eigenvalues and eigenvectors in a lower division course. Do you know why? In physics or engineering or something. Do you know why you won't? Because this class isn't a prerequisite for lower division classes, right? This is a second year class, so you can't make this a prereq. So you won't see eigenvalues and eigenvectors in freshman and sophomore level courses, and that's because freshmen and sophomore don't know linear algebra yet. It's not because linear algebra isn't important. I just want to give you that note. The reason why you've never seen it in science is not because it's not used. It's because you have to have this class first, and yet no one's had this class until they leave community college, basically. So, but now that you've at least had some of this class, you might understand some of this. So you ready to listen? It's going to go about 5 minutes, I think.
So this is the matrix that represents Sn, where theta is defining the direction of n. And now all we have to do is say that this matrix cos theta minus I sine theta I sine theta cos theta on AB is equal to AB. this eigenket, this vector has to be an eigenket of this matrix with eigenvalue 1 in order that it's an eigenket of Sn with eigenvalue a half, right? Because the original expression was Sn on this equals a half of that, but here is a half, I can cancel on the two sides. So I'm looking for the eigenket of this operator with eigenvalue 1. Notice I don't waste my time finding out what the eigenvalues of this operator are, this matrix are. I know that the because this is a matrix that represents a spin operator, Sn, I know before I start that the eigenvalues are plus and minus, well, of this one plus and minus a half, of this one plus and minus 1. So we don't waste time finding out what the eigenvalues are. We just get on and solve these equations. There are two equations here, but because we're looking at an eigenvalue problem, only one of them, these two equations are linearly dependent upon one another. Only one of them contains useful information. The other one repeats that information. So we merely need to look at the top equation, and it says that A minus 1, A times brackets 1 minus cos theta. So if I'm going to get A cos theta equals A on the right-hand side. So if I go on the right-hand side, we'll have A cos theta, A into 1 minus cos theta is equal to minus I B sine theta. In other words, we're going to have that B over A, which is all that I can, it's only the ratio of A to B that I can determine out of this. The absolute values have to be determined from a normalization condition, are equal to B over A is equal to 1 minus cos theta over minus I sine theta. And we can clean this up a bit if we use some half angle formulae, because this on the top is twice the sine squared of theta over 2. Sine theta is twice sine theta upon 2 cos theta upon 2. So we can cancel a number of things. The 2's cancel, one of the sine thetas cancel, and we end up with sine theta over 2 over minus I cos theta over 2. So I can write now that AB is equal to cos theta over 2 I sine theta over 2. So if you work out the ratio B over A of these two, I think you will get that, because this minus I can be put as an I on the top. And moreover, this thing is correctly normalized. It just happens. So in principle, I would now need to deal with the normalization. I've only been calculating the ratio of the components. I want mod A squared plus mod B squared to come to 1, but it jolly well does by good fortune, right? So this is the complete bottom line. This gives you, okay, right. So the probability that we pass F2, given that we passed F1, is actually equal to, we said it was going to be mod A squared, is therefore cos squared theta upon 2. Does that make sense? If theta is equal to nothing, then the second filter is also measuring the z component of angular momentum. And the output from the first filter is guaranteed to return plus a half for the z component of angular momentum. So this probability must be 1, and indeed cos squared of nothing is 1. If the theta is pi, then the second one is plus a half, then n is pointing in the minus z direction. So getting plus a half in the direction n is equivalent to getting minus a half in the direction z. But we know for certain that we're going to get plus a half in the direction z, so the probability of this happening is 0. And indeed, cos squared of, if I put theta equal to pi, I'm looking at cos squared pi upon 2, which is nothing. So that makes sense. If I put theta equal to pi upon 2, then we're measuring, then the n direction becomes the y direction, and we're measuring in a direction which is orthogonal to the z direction. And then you would think that knowing what components of the angular momentum in the z direction was couldn't possibly affect the angular momentum in the y direction. So you would expect that there was equal probability that half the probability of passing the second filter, as I say, of getting plus a half for the spin along y, that plus a half on y and minus a half on y would be equally likely by the symmetry of the situation. And indeed, cos squared of pi upon 4, or cos of pi upon 4 is 1 upon root 2, to cos squared of pi upon 4 is a half, and that makes perfect sense as well. So this formula predicts the kind of thing that you would expect.
All right, what do you guys think? Any questions? I know this was tough because he was talking in a different language, using things like Z instead of Z, and doesn't believe in saying the number 0. Also, did you notice he had eigenvalues, and did you hear the other word he used?
It was like some short 3-letter word. Eigentent?
Eigenket.
Yeah.
And that's kind of one of the weird things that happens when you leave math and you go to science, is that they have their own language. So eigenvalue is like the math word. And then if you're a physicist that is a quantum physicist, you use eigenket. But on the other hand, if you're in electrical engineering, you use eigenvalue. So it's not even all of physics uses ket. Ket is for quantum physics. And again, I'm not here to teach you quantum physics, but I did want to show you, that this is a course on quantum physics, and they use eigenvalues and eigenvectors. Without them, you really can't do it. You really can't understand orbitals and all that kind of stuff that you learn in chemistry, but never learn the mathematics of. And the reason is that you have to have linear algebra to be able to understand the mathematics of the chemistry that you took and the physics that you took.
I have a question. The angles he was referring to, was that the direction in which it was spinning, or?
Yeah, that's what's called the spin angle. And you got to be a little careful. It's not spinning.
Yeah.
It's just a word they use. There's nothing spinning. You can't even see it and see it move, because that would, you know what that does, right? If you can see it and see it move at the same time, you've broken the Heisenberg uncertainty principle, right? You've heard of the cat in the box. So the word spin is just a word they use, but it doesn't mean it. You don't picture anything spinning. It's just a word. So quantum physics is really abstract, but then it's really useful for all kinds of stuff, especially like hardware, computer hardware. You got to understand quantum physics to be able to do a chip, to be able to produce a chip, and memory and stuff like that, and all kinds of other things.
I have one other question for you. We know that quantum mechanics works. We use it. We know relativity works. We see it. Why is it that there are sometimes the two contradict each other?
So there's a lot of theories on that. One, believe it or not, I was one of the original experts in, is string theory. Is that if you move up to a higher dimension, then it actually works all together perfectly. But the problem is you can't test it, because we can't see anything in higher dimensions if there is a higher dimension. So that's one problem. So the reason is we know it. We know that's true. So that means our model isn't abstract enough, or isn't detailed enough. You can't keep it so simplistic. Does that make sense?
Yeah.
So you may need to go into multiple dimensions, in higher dimensions, or you may need to add in other forces and other equations. And no one really knows, because we can't experiment. Does that make some sense? But again, that's, there is linear algebra involved in that, a lot of it, but too hard to even talk about, if that makes sense. So we have a little bit of time. So let me unshare, but you were able to see and hear this? This is the first time I've ever done this.
Yeah, it worked good.
Oh, good, good. I think
Yeah.
it's because I have this outside microphone. If I use a computer microphone, it doesn't work. I've never been able to figure that out, but with the outside microphone, it seems to work. Kind of cool. So I've learned a little bit today that it works. So let me go ahead and move to, takes forever with Zoom because the Zoom stuff is blocking everything I want. Let's see if I can, it's 9, that's 7. I think that's the wrong 7 though, yep. A little higher on 7. Spectral theory, not yet. I think that's the one. No, 7.2, that means I'm almost there. Okay, so maybe I'll do an example for you. Maybe one of the later ones. And then let me do this too. Okay, so we're in 7.1. I'll let you pick a number between 9 and 19. First person to pick is the one we'll do.
12.
12 it is. Okay. So find the eigenvalues and eigenvectors of this matrix. And they give you a hint. One eigenvalue is -2. Why do they give you this hint? Anyone know? Why it's going to really help eventually to know that?
The polynomial might be a little bit gross later on.
Yeah, we're gonna have a third degree polynomial set equal to 0. We're gonna have to solve that. And if you know one of the roots, then you can always divide. If you know what root is, if you know a root is -2, then you can always divide by x plus 2, and then you'll get a quadratic. And quadratic, you should all know the quadratic formula, okay, or how to factor if it's factorable. So that's my guess why the author decided to be nice to you and give that to you. So let's do that. So I'm popping it here so I can type. Okay, so what's the first step?
Determinant of A minus lambda I.
Yeah, so we take the determinant of A, and A is, and I'm just going to do this together. I'm going to do A minus lambda I. Are you guys comfortable jumping to that step right there?
Yeah.
To just subtract lambda I by subtracting lambda from each of the diagonal entries? Are you okay doing that? Is it okay if I jump to there? It just saves a lot of typing.
Yeah.
Or writing if you're writing. Okay, so that 6 becomes a 6 minus lambda. And then, 76, 16. And then -2, -21, -4. Okay. By the way, yeah, I think I'll just do it this way because there are other possibility things that we can do, but 2, 64. I want 21 minus lambda. and 17 minus lambda. Kind of messy, right? Or maybe very messy. Okay. You could do some RREFing, but you got to be careful when you do that. So there is a way of doing it that way. I think I'm just going to do it directly. How do you find this determinant?
Is it called the adjoint?
Yeah, we're going to expand. Let's expand across the first column because those have nicer numbers, don't you think?
Mm-hmm. Yeah.
Of all the columns or rows, I like that first column the best. And I always like to go with the easiest. Okay, and so let's do that. So we're going to take 6 minus lambda. Times negative 21 minus lambda times 17 minus lambda. I'm going to just save some time. I'm going to make that 21 plus lambda. Times lambda minus 17. I just multiply both by -1, which I'm allowed to do. Just makes it a little prettier. And then minus a minus is a plus. 64 times 4 is 256. Okay. And that's the first one. Now we go to the next one. So then we have a plus a minus 2, which is plus, a minus a minus 2, which is 2. And then we find the determinant of that minor, 76 times 17 minus lambda. Okay, and then 16 minus 64, and it's a minus. 1,024, right? Is that what y'all get to when you do it in your head? Okay, and then we're going to have plus 2. And then we're going to take this determinant minor, 17 times -4. 304, sound right? And that's negative. And then a minus, and I'm going to just do a minus, and I'm going to multiply this negative, multiply the minus into the 21 minus lambda. So that gives you plus 21 plus lambda times 16. And then what's the final piece I write? It's easy. That's the hint. I just did all the hard part. Did you all give up? All right, maybe you're tired. Equals 0, because we always set the determinant of a minus lambda I equals 0. Okay, this is messy. Do you agree?
Yeah.
Yeah. What should you do at this point, honestly? Realizing I'm not an evil instructor.
Use a calculator.
Yeah, but I believe in computers more than calculators. Yeah. Use
Yeah,
a computer.
well, I mean like an online calculator.
Yeah. So use the computer calculator. Symbolab does this just fine. And by the way, you don't need to call it lambda. You could call it X if you want. Lambda is just the standard letter to use. I think it has to do with the wavelength idea. It's a wavelength of light stuff, and lambda is used for that. So I think the physicists got to it before the mathematicians. Otherwise, we call it X. And again, I don't have time to work this all out. But if you work this all out, you'll get a couple numbers, right? And that's it. Okay. Once we get the number, in fact, with the number -2, I know that's one of the answers, right? What do you do with the -2? What do we do with that -2?
Divide each factor by x plus 2.
No. If you're going to use symbol lab or something, you don't have to bother with that. Because you got your 3 eigenvalues. If we want the eigenvector that corresponds to the eigenvalue of -2, what do we do with -2?
Multiply it or add it into our lambda.
Yeah, not add it, but substitute it into.
Yeah.
Substitute the -2. So that 6 minus lambda becomes an 8. -21 minus lambda becomes a -19. 17 minus lambda becomes +19. And then at that point, you can RREF the matrix. And then you'll get one free variable. Okay, as long as the multiplicity of -2 is 1, then you know you'll get one free variable. And then let the free variable be 1 or whatever the common denominator is, whatever you want. And then you'll get your eigenvector. Does that make sense?
Yeah.
This is similar to the one I gave you, except that the book is more evil because it gives you uglier numbers. Maybe you think I'm evil too. I gave you ones and negative ones. Because even a 3x3 gets really messy, really fast. Do you agree?
Yeah.
Okay, so now we're out of time. So I'm going to stop the recording. Actually, stop the share first because it's easier. Oh, shoot. And stop the recording.